Next up is Josh Rosen, an incoming graduate student in the AMP lab who's been hacking on the Spark Python API and Spark Java API. He's going to talk about the Python API. He's been hacking on the systems, and that's what he'll continue to do as a graduate student.
All right, hi everybody. Thanks. Today I'm going to talk about a new experimental Python API for Spark. It hasn't been released yet, and it's not in the development branch quite yet, because we're still working on adding features and bringing the performance up to par. But I can give you a quick preview of it today. So the new API is going to be called PySpark. And at a glance, it's going to let you write your Spark jobs in Python. And we support all of your Python features, CPython, C extensions too. So all of your Python libraries will work. We're not using a solution like Jython that limits the libraries that you can use. We are also going to have an interactive shell that's just as easy as typing at the regular Python console. So why don't we just jump right in and take a look at what some PySpark code looks like. Here's the word count example that you've seen a few times. As you can see, it looks a lot like the Scala code. It's a little bit more verbose. You have to say lambda here or there, but not much. It's pretty compact. So probably the best way to give you a sense of the API is to take a look at the interactive console. So we can do a few demos here. So the first step is to create a Spark context object, just like in regular Spark. And I'll create a local one with four threads. And it starts up the Spark context for me. And we'll just parallelize some numbers, say 1 through 20. And I've got an RDD. And as you can see, like regular Spark, operations take place lazily. So I can say map this, just multiply everything by 2. And it's lazy. It's not calculated until I actually do something that requires computation, like grabbing the first number or grabbing the entire collection. So as you can see here, I was able to just write a lambda function. I didn't have to declare my functions in a separate file. It just got serialized and shipped across the network to execute with no additional work on my part. We also support other functions too. You can write a reducer. If you want to calculate a sum. So this is pretty flexible. And you can see that it supports a lot of the methods that regular Spark does. Not all of them yet, but you can do Cartesians, you can cache things, you can take samples. Oops. Yeah, so this is pretty easy to use. So let's take a look at some more full-fledged programs to get a sense of what a complete example would look like. All right, so here's a k-means example, a complete example in PySpark. We have a couple of utility functions here for parsing vectors out of a file, and for given some centers and a point, finding the point that's closest. And then here's the core of it. We create a Spark context. We load a text file. We support all of the same file input and output as regular Spark, so you can load files out of Hadoop, your local file system. Then we map it to parse our vectors, and we can cache it. And then in this loop, we actually do the work of finding the closest points, summing up vectors and points, dividing to find the centers of each point, and propagating that through. One cool feature of this is that we're using the NumPy library, a high-speed numeric library that's written in C. So we can use C extensions, and that works fine. Another cool feature of this is it shows functions that use closures. If you see this function here, this lambda, where we're calculating the closest point, we have this k-points variable, our current points. And so that appears in our closure, and it's automatically serialized across the network. So there's no having to write special subclasses like in the Java API. You can just write your code naturally like you would locally or in Python, and everything just works. So let's see what this looks like if we run it on just a very small example file. And there's our final centers. As another small example, we also have, there's the complete word count example. We also have another example, computing pi, by generating a bunch of random points and seeing how many fall within a circle. So there's a few examples there for you. So let's take a look at how this is implemented. It's not very much code, actually. The whole Python API at this point is maybe 300-400 lines of code, which is surprising for how many features it has. So here's kind of a high-level overview of how PySpark works and how it's built on top of the existing Spark core. So you write your job in Python. And when I created that Spark context object in Python, behind the scenes, it's spinning up a Java process on my local machine. And inside of this Java process, we're running a copy of the Java version of Spark. And there's some communication that takes place between our Python process and Java using this library called py4j over kind of a local socket. So our Python data is passed to py4j, where we just call into the native Java methods. This serializes our functions and our data, builds the kind of RDD, and then ships it across the network to the Spark worker machines. And we use a kind of a modified custom RDD subclass there that takes the data and pipes it out to a Python worker process on each machine that performs the actual execution. Then the data is piped from the Python process back into Java, and then finally back to your machine or for further processing. So internally, your RDD, your data from Python is serialized using the Python pickle library, and it's stored as an RDD of serialized objects. So that's how we're able to use built-in partitioning and sampling techniques in Spark. And actually, I can give you an example of that. You can see, if I just swipe over here, you can see what an RDD looks like in its internal representation. So here I'll just kind of peek behind the scenes and take a look at the Java RDD object that's actually backing this inside of that py4j library. And if I actually collect this, you'll see that it's actually some byte arrays representing my data. And that's the same for the other Python types too. So under the hood, all their data types have one uniform representation, pickled Python objects. Oh, one cool thing. This is dynamically typed like Python. So because we don't have any type checking, I can do things like this. I can have strings and integers and tuples or whatever mixed together. So I talked about how we serialize your Python function to distribute it to the workers where it can execute. That's actually kind of non-trivial to do in Python. So the regular Python pickle serializer can't do it. We're using a library developed by a startup called PyCloud, and they've kind of solved this kind of very tricky problem, especially when you have a function that might be recursive or have other functions in its closure. It's really hard to make everything just work, but we've taken care of that. So the serialization cost of serializing these Python objects and piping them back and forth is the kind of dominant performance issue at this point, and we've taken a lot of steps to try to optimize that. So one of the big steps is pipelining Rdd transformations. So like what Spark does, if you have Rdd transformations like a map followed by a flat map or a map followed by a reduce, operations that could be performed on the same machine before any communication has to take place, we compose all of those together and execute it in just one Python phase. So this means that we can cut out a lot of serialization. We don't have to make unnecessary round trips from Python to Java and back to persist our data. So this makes a large performance difference, and we're kind of working on adding more pipelining. And of course, this makes intelligent decisions with caching too. If it sees some of your intermediate RDDs are cached, it won't just unnecessarily recreate them just for the sake of pipelining. So I said that this is built on top of the Java API, and one feature that we have planning is tighter integration between the Python and Java APIs to let you write your workflow in both. So using that Py4j library right now, if you have an existing Java or Scala Spark workflow, you can package that up into a function and call it, and you can obtain that Java RDD from inside of Python, and then you can do further processing on it. So in fact, you can actually write all of your data processing code in Java and just use the Python to launch your jobs and pipe a few variables in here or there if you wanted. So we support it in that direction, and we're also looking into how to take your Python-created RDDs and get it back into Java. And that might involve mapping it down to a text format or JSON or something like that. So that's just kind of a quick overview of the main features of PySpark. We have support planned for a bunch of other features that are in Spark that we don't have implemented yet, including accumulators and broadcast variables, looking at more input and output formats. Another interesting thing that I've been looking at is trying to rely on the native Java methods to speed up certain operations. So you saw those serialized representations. I'm using this serializer called Pickle, the kind of built-in serializer in Python. Well, if we have a situation where identical objects serialize down to identical serialized representations, then you might be able to do certain operations like join or removing duplicates, things like that, without ever having to touch Python, because you can just operate directly on the serialized representation and never have to call out to Python to decode it and perform comparisons. So that's a little bit tricky. You have to make sure that your serialized representations are identical, and it's kind of non-trivial to do with the Pickle serializer due to some details of how it's implemented. So that's one thing we're looking at to kind of improve performance. Custom hash partitioning, other things like that. So that's a quick preview. This is not on the dev branch yet. It's in my GitHub repository. I'm sure we'll make an announcement when this is available and ready to use. Does anybody have any questions? Or yeah.
So if I want to use a C library, would it be preferable to use the Python API for that? And would that library be shipped across to the workers? Or should I use JNI for that?
That's a good question. So the question was, if you want to use a Python library, should you use JNI or C library? Should you use JNI to interface with it, or should you use it in Python? So if you want to use a C library in Python, there has to already be a Python binding for it. So I imagine it would be faster to use the JNI binding, that there would be less serialization taking place. It might be a little bit faster, but I'm not certain. Anybody else? Yeah.
So how do you handle shipping Python libraries to the workers? Is that taken care of through some tarballs or something like that? So
that's something I'm still looking into. So the question was, how do you handle shipping of libraries? Do you use tarballs or something? So you obviously don't want to be shipping like a big heavyweight library in every single call. Although shipping a small user-defined function is pretty small, that's okay. So I'm looking into that. Maybe I'll use a solution like virtual env. I do have a way to actually specify which Python executable is used and pass some options to it. So if you wanted to use, say, a different Python environment like PyPy that uses just-in-time compilation, you can do that. So yeah, so you'll be able to configure your Python environment on your worker machines and point PySpark to that end. Anybody else? Well, great. Thanks, everybody.
Thanks, Josh.